Greetings and welcome to our presentation entitled Robust Observer Design with Prescribed Settling Time Bound and Finite Varying Gain. My name is Ramon. I'm a PhD student at CITEDI IPN, and this work is co-authored with Dr. Yuri Orlov from CICESE and Dr. Luis Tupac Aguilar from CITEDI IPN. The outline of the presentation has 5 items. Let us start by the motivation. In this slide, I will show you 2 examples of critical convergence time application. In the left, we have the stabilization of the working of a biped robot. This one should take place before each state in the robot. And in the right, I'm showing you a missile intersection task. In this case, of course, the control goal should be fulfilled in the short amount of time. There are some examples on finite, fixed, and prescribed time stabilization in the literature. I'm showing here in the equation 1 an ordinary differential equation with a settling time function that is upper bounded, like here in 4, but as you can see, it depends on the initial conditions, and this is what I'm showing you in the right. For several initial conditions, trajectories are stereo to the origin, but that setting time function depends on the initial condition. Going further in the research, in the literature, we can find also fixed time stabilization. In this case, I'm showing you here in 5 a differential equation that possesses a settling time function given in 8 that is upper bounded regardless of whichever initial condition the system starts with. In this case, it's upper bounded by pi, as I'm showing you here in this video. But sometimes it's not as easy as here to find this upper bound for the settling time function. That's why recently prescribed time stabilization has been addressed. In this case, there is a parameter, design parameter, capital T, that is predefined by the user and constitute the setting time, the upper bound of the setting time function for the system presented in night, for instance. As you can see here, it doesn't matter the initial condition, the trajectories of the system are always stereo to the origin in a time no longer than capital T1. So the problem statement in this case is we have a system in normal form given in 14, where matrices lambda, b, and c are given here, and eta is a state vector. Eta super 0 is the initial state vector. E sub 0 is initial instant. U is the control input, and w collects uncertainties and disturbances. And finally, y eta is the only available measurement. We will assume throughout that the external disturbance w is of class L infinity and possesses an a priori known magnitude bound capital L such that this inequality here is satisfied. This upper bound capital L is also a known constant. So the problem is to meet a prescribed upper bound capital T on the observer convergence time independently of the initial states and regardless of whichever admissible disturbance W affects the system. The solution we are proposing is based on the following hybrid observer. The hybrid observer is defined in 1516 together with mathcal M, capital G, lowercase g sub I, f, a transpose, and the time varying gain mu sub 1 inherited from the previous work from Song et al. In the ingredients of the autonomous substructure based on the plant that we're considering, the estimator algorithm given in 18. This estimator algorithm, the adjacent terms are inherited from the previous work from Levant, and the observation error tilde eta 1 producing the observation error equation 19, which provides the estimation to be equal to the real state in finite time as long as the gains k sub I are chosen as in Theorem 1 in Cruzabala et al. So this is the ingredients of the autonomous substructure. The ingredients of the non-autonomous substructure of the observer are the time-scale transformation S, its time derivative with respect to time to t, which produce time-varying gain mu sub 1, and its inverse t depending on S. A plot in the left is showing t of S versus S. So the design in S time, for instance, how we do obtain this observer. We start with the observable system in by diagonal form presented in 20, where capital lambda is given here, b and c are these matrices, and the bidiagonal matrix A is composed of capital lambda and a diagonal matrix with elements delta sub I this delta sub I element will be the final leg. This structure is known to possess the observation matrix as I'm presenting here. The second step is to transform to a system in observable canonical form by using the transformation 2, which produce a system in observable canonical form 3. In this case, math call A is given here, as you can see, as a matrix in observable canonical form, plus capital delta. This result, this new system in observable canonical form possesses an observation matrix math call O2. Now we can compute the transformation matrix P. The third step consists on design an observer for the system in observable canonical form 4, and the resulting observer is given in 5 with f capital G and its components lowercase g sub I given here. The last step in this case is to design an observer for the system now in bidiagonal form. To do this, we can go back. We can use the inverse of the transformation of the coordinate transformation 6, and we will get an observer for the original system in bidiagonal form 7. In this case, f, g, and g sub I are specified as I'm showing here in the right. Now we have an observer in the S time in bidiagonal form, and we need to go to T time, for instance. So we are going to do is to, starting from the observer in S time presented here in 9 for the system 8 with observation error 10, we will define the bidiagonal matrix A by setting delta sub I as I'm showing here. Then we apply a time scale and state transformation as I'm presenting here in 11 and 12 respectively by using this time foreign gain mu sub 1 already defined. With this time scale and state transformation, we will get the observer for the system in normal form with prescribed time 13 and injection terms given in 14 with a non-autonomous component as long as we do not detect the sliding mode to start and the autonomous component after the sliding mode is detected. This theorem resumes the previously discussed procedure. Consider system 20 and its observer here below, which is specified with P, F, G and lowercase g sub I and an arbitrary small capital T, which will be the upper bound of the finite function. This is independent of initial conditions and unmissable disturbances. Then the aerodynamics 21 are fixed time stable with a convergence time capital T sub 0 lower than capital T and with bounded mu sub 1, the time varying gain, which is applied at the initial stage 0 capital T sub 0 only. In this section, we show an illustrative example and also we do some comparison with prescribed time and fixed time observers from the literature. The example considers a plant of a third order with capital lambda defined here and also B defined as here, and the only available output is the first state of a system, which is also affected by a measurement noise. This plant is specified with known and unknown but bounded inputs U and W respectively. Quote, this perturbation is upper bound by 0.2. For adding practical value, the presence of measurement noise fees in the observation channel is considered. The observer, according to the theorem we already showed, is given as here, defined with these matrices, and the observer parameters are defined here. Notice that the upper bound and also the sign parameter capital T is set to 1. So observation error trajectories are expected to converge to the origin in a time no greater than capital T. These injection terms, the autonomous injection terms, are selected like here, and the gains K1, K2 and K3 and also L are chosen accordingly to the work from Cruzabala and Moreno. The observer injection terms that are brought from the literature can be found in the theorem 1 in Holloway et al. And are given here. Q sub 1, Q sub 2 and Q sub 3 depending of these time varying magnitudes gamma 1, gamma 2 and gamma 3. Also, it's defined with parameters as I'm showing here. Notice that the capital T in this case for the observer in Holloway et al. is a little bit extended its value to avoid numerical issues, as also mentioned by the author Holloway and Krstic in this work. The fixed time observer is brought from Theorem 2 in Menard et al. With observer injection terms as I'm showing here, Q1, Q2 and Q3, and parameters as I'm showing here in the bottom of this slide. The simulations are conducted using MATLAB Simulink with initial conditions for the state of the observer at 1 in every state, Euler forward integration method, and sampling time as I'm showing here. The time response of the prescribed time and the prescribed time finite gain observation errors is shown in this slide. For instance, we have tilde eta 1, tilde eta 2 and tilde eta 3 in this slide. As we can see, both observers are converged to the origin in the prescribed time, but we have a non-desirable incidence of the measurement noise in the prescribed time observer from Holloway et al. This is due to the convergence in this case is at the prescribed time capital T and not before, and in that moment they are suffering from a high gain issue. That's why they are highly amplifying this measurement noise, which is not the case in our proposal. The injection terms, of course, are also suffering from this drawback in the case of Holloway et al. As you can see here in the red line, the injection terms from Holloway et al. Are suffering from this drawback. Nevertheless, in our case, these drawbacks are not present. Now we are presenting here the comparison with the fixed time observer, and this slide shows the observation errors. In this case, what we can see here is that both observers converge to the origin as decided before the capital time. But what we can see here is that the time response, the transient of the time response is really high for the observer for the fixed time observer from Menard et al. This is in contrast with our observer that presents a lower magnitude of the transient response. The injection terms, of course, reflects this high transient response for the fixed time observer, and can be seen, its values can be seen here. They are very high for the fixed time observer. This let's say this drawback is not present in our design, for instance. Now we are ready to present some conclusions on future work. Non-autonomous fixed time observer design was proposed for an arbitrary order normal form system with a prescribed upper bound capital T on the observer convergence time. The resulting observer gets a bonus of operating with uniformly bounded time varying gains over the entire infinite horizon, and it is therefore straightforwardly implementable in a similar manner to its finite time progenitor. This is in contrast, for instance, to Holloway et al., facing infinitely large time varying gains as the time gets closer to the prescribed time, and thus manifesting the high gain challenge of the observer implementation. In comparison with the prescribed and fixed time observers of Holloway et al. And Menard et al., the developed observer was shown to possess a lower sensitivity to low magnitude with high frequency noise added to the measurement channel. Extension of the present development to prescribed time output feedback stabilization with uniformly bounded time varying gains is among challenging problems calling for further investigation. Thank you so much. We left here in the bottom contact information in case of any further discussion.